But once you can write code behind the buttons or behind the screen, in other words, where do you put logic? Do you put it in the PLC or do you put it behind the HMI? The answer is where do you want to put it? Because it can be either way, it can be either place. Typically, the things that make the machine run, that have to be there for the machine to run, you put in the PLC. But anything else, it's up for grabs. Some of it you might put in the HMI panel. You write script, you can write it there, or you can write it in the PLC. You can write script in the PLC too, either one. So that's kind of an aside, but it is important that you at least know about it. Okay. Okay, now I'm looking for that. Bit of digital logic. It's thinking. A computer's cold. It must be. It's what must be cold. It's slow. Very slow. Okay, so we want to go down to chapter 4. Now, I mentioned just in passing about kernel maps, and you can minimize a Boolean logic statement with kernel maps, and they are useful, but I'm going to say this kindly, but I never used a kernel map in all the years I programmed. Why did I not use kernel maps? Why did I never use a kernel map? This is a simplification process for a Boolean expression. You can simplify any up to 4 variables with a kernel map. And I'm going backwards because I want to find uh, De Morgan, which is a little bit above this. And it's still leaving me. Right. It's up here. Why did I not ever use a kernel map? Well, I'm going to find it eventually. Here it is. This is a section that I'm going to hold you responsible for. Okay. Why did I not? Yes. Why would I? Yes. It's under MIME 4550, a bit of digital logic. Okay. Why would I totally ignore Carnot maps for you and in general? How much do you think, once you get something to work, that you would ever pay somebody to change it, to simplify or to minimize it? You do not do that, because if it works, don't touch it. And also, memory is cheap. There's no reward for using a slightly simpler circuit. If the one that you've got works, leave it alone. Don't try to minimize it. If you do, you're wasting your time and you're wasting your company's time. Okay? Simple, but Carnot maps do simplify circuits, and you can use it to simplify circuits, and you can use this as a method for doing that. But in general, you don't do that. I never, ever did a Carnot map. Okay? And I did all kinds of logic. I wrote all kinds of circuits, logic circuits for all kinds of things. Never, ever did it. I have done this, though, the De Morgan, okay? So with De Morgan's theorem, it basically says this. Now, if I have an expression and I put a bar across the combined expression, that says the knot of xy, okay? The knot of xy. Now, what does De Morgan's theorem say? It says to basically break the knots until they're only over single items. And the rule basically is this. If you have a knot over an and, to break that, you have to break it into the or of the knots. So the knot of xy is equal to the knot of x or the knot of y. And you can prove this. How do you prove it? Make x a 0, x a 1, y a 0, y a 1, and these two functions are identical. If you prove it by taking through all the ways you can do it, it's that way. Okay, so this is the general philosophy. We want to break the bar down to single individual items, not bar over multiple items. Only single items are as allowed. So if I say take the De Morgan of this is the answer. Bar over individual items, not over multiple items. Okay, so here is the corollary to that. This is the other one. The bar over the or function is the not and of each, not x and not y. Any questions about that? So when you break something, you flip from and to or to and. Okay, well here would be one other one. Here's a threefer, x, y, and z. Knotted is the knot of x or the knot of y or the knot of z. Okay? And the knot of x or y or z is the knot of x and the knot of y and the knot of z. So you can see this gets kind of interesting. And these are good problems. And you can go through this and you can say, now, how would I do this? Well, here again. What's the answer? The answer is when you have not bars over individual items only, not over combinations. So the answer to this is this and then this. Everybody see that? And you can have double bars. Oh my goodness. How do you do that? Well, you work the inner bar first and then you work the outer bar. So how you do that is, the answer is you do it very carefully. You do the inner bar and then you do the outer bar. Now, what's a double bar? What's the double bar of something? If I had F double bar, that's equal to just F. Okay? So you can take, if you get a double bar, it's the knot of the knot, which is basically back to the original signal, whatever the original signal was. What could the signal be? It can either be a 0 or a 1. That's all it can be. These are binary variables. So we're talking about binary variables. They're either a 0 or a 1. That's all they can be. And that's all this is. We're not talking about higher level math. It's a 0 or a 1. That's all this is. Any questions about this? What's your quiz going to be on this week? Duh. It'll be one of these, okay? So I'll give you one of these probably tomorrow, next day, sometime to hand in next week. give you some practice with this. Make sure you've got this down. So you can do this in either Boolean, or you can do it in ladder, or you can do it in the gate format. I prefer it in ladder, but this book only does it in Boolean. Okay. Now, if you look in my chapter 5, we'll practice some of those in ladder. So there's some questions in chapter 5 about De Morgan that have to do with ladder logic, but they're the same thing. Why did I put that into chapter 5? Well, I want you to understand De Morgan, but I also want you to understand the transferring of logic from Boolean to ladder, and I want you to be able to make that transformation. And now, if you are at the stoplight and you're thinking about this project that you're working on, or this problem you're going to hand in, and you're thinking about it in Boolean, that's not what I would be thinking. I would be thinking about it in ladder. But if all of a sudden you flip over and you're starting to think about it in ladder, I won, because now all of a sudden you're thinking about it in the language, in the format of industry. So you're basically flipping over from thinking about it in this language called Boolean, which is this is a language right here, right? That you can basically take this to the bank and say this would be an expression you can put into a statement in a procedural language, but it doesn't look like ladder. And I want you to think about it in ladder. But right now, for this term, right now, I'm going to give you something like this. Okay. Now I want you to think about it for a second, because the other day I told you that I was going to give you an example of a program that's here, that's in chapter 7, and it's several of these programs, several of these labs have they have options. Now the reason I put in a lot of options was because every time that I went through these labs with a different group of people, I didn't expect them to take last semester's lab and hand it in for this semester and you get credit for it. So for a while, I would keep creating new options. And then I settled on a few that I really liked, and the rest of them said heck with. But basically, there's an option in the traffic light program that proves that if you can think De Morgan in ladder, you win. And I'm going to show it to you right now. Okay, so basically, we've got this traffic intersection problem, and there's 3 directions. You can go north, south, you can go east, west, or you can go to turn lane. Okay, so there's 6 lights. Well, there's 6 time segments, there's 9 lights. So if you look at it, there's red, yellow, green, north, south, red, yellow, green, east, west, and then red, yellow, green, turn. So in that entity, there's 6 time, and again, I know that there's a little delay between when the one turns red and the other one turns green. I know that, and I'm going to ignore that. Okay? I'm just going to say, at the end of this time period, you go to the next one, then you go to the next one, you go to the next one, and then it repeats. All right, so basically what I'm going to do is I'm going to set up a repeating time circuit, and I'm going to do it like this, okay? The knot of the first one goes to this. Now this would be my first timer, and its output is, let's call this T1, or this is T1, and then that's time 1 done. Now that's the Ellen Bradley output. If you're a Siemens person, it would be T1.Q, but they mean the same thing. These are equal. Now, so when T1.done is when you're done with timer 1, it executes timer 2. And then it has a bit called T2.done. And then you can see the pattern, right? You can say, okay, The second one gives me the third one, the third one gives me the fourth one, the fourth one gives me the fifth one, the fifth one gives me the sixth one. And then what happens when the sixth one turns on? When the sixth one is done, T6 dot done, what turns off? Bingo! T6 dot done turns on, turns that one off, and it all falls apart like a house of cards. You've all built a house of cards, right? What happens when you pull the bottom one out? They all fall down. They all go back to zero. Does everybody see what I built here? Timer 1 takes a little while for it to turn on, and then after it's turned on, after it's done timing, this bit turns on. This bit turns on this one, which does timer 2. This bit then turns on, which turns on timer 3. This bit turns on when timer 4. This bit turns on timer 5. This bit turns on timer 6, and so forth. And when you're done, then you can also show what the lights look like when you're done, okay? So this is not a tricky circuit. I really encourage you to build this one. This is a chapter 7 one, and it's a good one to see how timers actually work. But come along with this option. The option is to add a timer 7, that occurs only when somebody comes up and says, everybody walk. So a pedestrian walk, Ted, it would be a 7th timer. So it's a free-for-all. Everybody can walk, all the lights are red, and we're all set. Okay, so that would be how that's done. Now, how do you do that? Well, you basically set up a memory circuit or a seal circuit like you did in the lab. That if you've done the lab for the relay, you build a little seal circuit or a circuit that looks like this. Or you can build it with set and reset. I don't really care. But so far, this is the only one we've talked about. This would be to turn it on. This would be the request, and this would be the walk bit, and this would be the seal. But what about that bit? We don't know yet, do we? So what do? Well, you keep going, and then you leave that blank until you figure it out, and eventually you'll come back and you'll find that there's something someplace that will actually turn that bit off. I don't know what it is yet, but I know that, trust me, there will be something that will come up in your logic that if you're working a crossword puzzle, you go back and you look and say, okay, if I do this, then I'll do this, then I'll do this, and I'll do this. And that's where you're at right now in the crossword puzzle. I don't know that bit. I do not know what that bit is going to be yet, but I do know it because I've done this a million times, but you don't know it yet because you haven't figured it out. Okay, so that's where we're at. Now, what turned this one off before? Timer 6, right? Right? So what now turns it on? What now turns it off? Timer 6 or timer 7, right? But it's not that easy. It's timer 6 turns it off if you do not have the walk on, but timer 7 if you do have the walk on. Does that make sense? Because that's what this is. This is logic, and you're having to go through and having to think about it. You're having to say, now what would it take for me to have that bit turn off? What does it take for that bit right there to turn off? It's not going to be timer 6 anymore. It's going to be timer 6 or timer 7, but it's not just timer 6 or timer 7. It's timer 6 or timer 7 with some other logic. So now I play the game, all right? This one's not easy. This one is one of those times when you basically are kind of, well, you can struggle with it and you can get it eventually. But I'm going to show you that, I hate to use the word cheater because you'll think I'm always using the cheating way of doing things. But I'm giving you an option of how to think about logic because you now know how to make the negative of something. Okay? How do you make the negative of something? How do you make, okay, if something comes, excuse me. If I have some logic, and I put the bar over it, that's the negative of it, right? So how do I do that? Well, now you've got the method of doing it. You do the De Morgan. If it's anded, you separate them by breaking the bar and making the other. If it was an and, you make it an or. If it's an or, you make it an and. That's as simple as it goes, but that's it. All right, so now, what did I just say? If I say the positive logic, it's easier than it is the negative logic. And I'm going to reiterate that. So let's say the positive logic for turning this bit off. The positive logic would be timer 6 and not of walk. Is that right? So this bit here would be timer 6 and the not of the walk. Correct? Or timer 7 and the walk bit on. Everybody agree with that? How would you write that? In ladder. Okay, how would you write that in ladder? Timer 6 dot done and not walk. Or timer 7 dot done and the not of, excuse me, and walk. Now, you can take this to a bit, call it x, and make this the not of x. That's one way of doing it. And that's fine, that's legal. But what would be the other way to do it? And probably the little bit, I would say this would be the little bit more, how do you want to say it? The better way to do it. Now, I'm not going to judge your logic ever, but what would be the better way to do this? This is positive logic. How do you take the negative of x? Somebody do that? Any volunteers? Well, think about it for a second. This is anded. The negative of that would be the or, right? And it would be, this line right here would be the not of T6 dot done. And it was anded, now it is or'd with walk. So this little piece here would be for this little piece right here, just this top half. Now what about the bottom half? This was or'd, now it is anded. Does everybody see that? So not of T7 dot done. Or this is anded, now it is or'd with the not of walk. So you put this logic right here, see if it works. I bet it does. So do you see where De Morgan actually can come in? If you think about something and you think about it in positive logic, and then you say, but I needed negative logic, you flip it and you're done. Make sense? That's why De Morgan is important, and that's why we're stopping and talking about it as opposed to just blowing right past it. Because it does make sense to use from time to time when you're writing logic. And you now are all of a sudden into writing of logic, and that's basically what this course is about, is writing of logic to do things real, to do real things, to do real projects, real live things that are, some that you will do a million times. If you program, you will be doing these again and again and again. And some things you won't do a lot of, but you'll be the only person who knows how they work, so you'll be the person who does it. Everybody understand why this and this are important? They're not critical, but every once in a while you use it. Anyway, and that's the last of the digital logic course I'm going to talk about. But I'll give you one of these like this to do for a quiz this week. I want you to be able to do that. And I probably will ask you to do a number thing as well. We'll figure that out. But anyway, those two things, just to kind of get at this. So now let's go back and let's look at chapter 3. Okay, so let's go back to the book. Chapter 3. Okay, so just talking about this book a little bit in general, and the so this hybrid text is a free book, and we basically have covered these two chapters, and now we're getting into the actual programming of the PLC and chapters 3 and chapter 4. Chapter 3 is kind of a walkthrough of how a PLC does the same thing as a relay. Okay, I've had people to do projects with the programmable controller, and they actually wire the logic externally, and then they take it into the programmable controller, and they think they're doing the right thing. That's not the way that the programmable controllers are working. The whole idea of a programmable controller is to do all the logic inside of it. Okay, so you don't want to have any logic that is being done that is not inside of it. And also, what do you call things? All of a sudden, what you label is important, and how you describe something is important. And that's in chapters 3 and chapters 4. And the labs in chapters 3 and chapter 4, the lab at the end of chapter 3 basically is a download of a nothing program, but it prepares you for when you actually do write a program. Now, here's the deal. Both of these programmable controllers, there are ways of transferring from one PLC to another PLC, but they're very cumbersome, and I don't want to get into those. So if you don't do a download of a nothing program before you actually start writing code, you can be writing code for a programmable controller that does not, you can't link to. So the best thing for you to do is to do the chapter 3 practice of a download of a nothing program. If you can download a nothing program to your programmable controller, then you can actually build a program that you can download to that program controller. All right? You've got to be very careful to do that the first time, because with Allen Bradley, they're all the same, but with Siemens, we have variety after variety after variety of PLCs in those labs. And every part of that PLC has to be explained explicitly in the building of the PLC, or it won't download. Okay? We have 1214 PLCs, we have 1215 PLCs, we have different firmware versions. We have external boards that are attached to them, or not. So you have to look at the program controller that you're using and be very careful. And then sometimes still you got to go fish, because you can have version 4.2, version 4.4, version 4.6 of the firmware on some of these program controllers in Siemens. That being said, all that being said, this is a barrel of fun. You can practice go fish all day long. I don't like that part about it, but I don't know how to cure it. And one person came along and said, why don't you turn it all to the latest version? Well, for one thing, I'm lazy. Another thing is you got to learn that there are different versions, and you have to, once you find the right version, then you clamp onto it and you're okay. But you got to get used to this, because these versions they're different, and you've got to be careful. So when I say in the video, go to version 4.2 or 4.4 or 3.1 or whatever, that may be the case and it may not be the case. So you have to be very flexible. And I'll give you some of the hints, but basically with Allen Bradley, you only got one. You can't mess up. The video is what is out there and it works. With Siemens, there are about half a dozen different varieties. And now that we're going to version 20 of the software, they'll all pop up differently than they do in the videos. So you're going to have to be careful. Okay. Now, all that being said, let's go to chapter 3. So this is what a PLC basically does. Takes in inputs, runs a program, and spits out some outputs. Okay. And that's nothing new. That's what a computer does, and that's what everybody's used to. And this is a different picture of it, but that's kind of what they do. And it solves the logic sequentially. All right, what happens electrically? Well, in an electric circuit, you hook something up, you have a switch, battery, turns on a light. Now, if you were to do that in a PLC, you would basically have a PLC program that you push a button, you got this, goes into an input, that input light would light, you would see the little light that comes on, an LED that says, hey, you're on. And you'd also have a light that says you're running your program. Your program is actually running. You would have a contact inside your program that says that input is in there, and it's programmed to an output. The output turns on, and it turns on the light. Nobody'd ever write that program, but that's how it's done, okay? It's got to go through this step in the middle. Now, there's about half a dozen things that can go wrong, and we aren't going to go through every one of them, but there are things that key. The program could not be in the run state, all right? That's a biggie. And the other kind of things that can go wrong is you can have it hooked to the wrong input or the wrong output. The address could be wrong. The light could be not hooked to a neutral. So these outputs turn on to 24 volts. Both of them turn on at 24 volts, off at 0. With the Allen Bradley, bless them, they've got a separate set of jumpers on the power when you bring your 24 volts over, there's a second set of jumpers. So they have an internal, what they call a master relay. If that is not wired, your outputs don't turn on. So if you don't have the second set of jumpers when you're bringing your power into the program controller, if you don't see the second set of jumpers, somebody didn't wire them in or they've been taken off for whatever reason, your outputs will never turn on because the master control relay is not on. So again, there's several things that can happen. Siemens doesn't have a master control relay. But anyway, Allen Bradley calls an I an in. Siemens calls an I an in. Allen Bradley calls an O an out. What does Siemens call an output? A Q. So get used to it. I's are ins. Allen Bradley, O is out. Siemens, a Q is an out. Okay, so this is how it's processed inside the program controller. And you have different types of I/O devices. You have different types of inputs and different types of outputs. These are some various types of inputs devices. And what is this? Is that an input device or an output device? The answer is yes, it's both. It has a light on the back and it has a push button. That's called an illuminated push button. And the push button and the light are not connected electrically. You can have them connected electrically if you want, but you can also take them as separate signals. The output can be tied to the output of the program controller, the light can be tied to the output of the program controller, and the input can be tied to something totally different that you push a button and something happens, or doesn't, whatever. But they are totally independent. All right. How do you run a program? How do you run a project? Well, you come up with an idea, You configure the controller. You got to buy the stupid thing first. You got to buy it and get it in. Now, you can have software that can run interactively that will, like I said, do the simulation for a while, but eventually you want a real program controller. So how do you try this stuff out in an office? Well, many times you do try the simulator out, and then you go out to the field, and then you actually try it out in the field and actually make it work there. All right? You compile it. After you add the logic, you compile it, get all the errors out. That doesn't mean that your program will run. It just means that it will compile, and then you troubleshoot it. And then back and forth between programming and troubleshooting, programming and troubleshooting, programming and troubleshooting, programming and troubleshooting until you get it to work. It's back and forth, back and forth, back and forth, back and forth, back and forth. You see it on the screen, something isn't working. You look at it, you see where it's not working, or you set traps. You have to get inventive, but you can do that. That's why they pay you. So the whole idea of going back and forth between these two steps is extremely important. Sometimes there is this issue of loading into a running program. So you can create, Alan Bradley does have a way of adding logic to a program that is running. So you can make edits online. Please, in this course, be very careful when you do that. Don't do it unless you kind of know what you're doing. One of the quickest ways to make a mess of your program is to try to make online edits. In other words, online edits, you have to go through about 3 steps. And you say, why do you have to go through all those steps? Alan Bradley, okay, so in a chapter 20 on safety, one of the things I go through is I go through a story from Siemens about how Alan Bradley did this big bad thing at some point in their history. They got sued and they had to pay $130 million, okay? Siemens told that story. Siemens basically is out telling that story. Well, they both have deep pockets. These are big companies and they have deep pockets. So if somebody can sue them and make $10 million, they will, all right? So if you are making an online change to a program, with Alan Bradley especially, you have to really, really want to make that change, all right? And there's several steps you have to go through to do that. And I don't really give you very much direction along those lines. So my advice to you is to make your changes offline, download them, and then put it in the run mode, okay? You can do online changes, but you have to go through several steps. And I'll tell you this, when I'm looking at somebody's program, saying, this thing won't run, and you got a ladder that's green, and then all of a sudden it's broken, and it's not green for a while, and you got dashes, 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 that's where you tried to make a change, but it didn't compile, and it didn't go through the test mode, and you didn't get it to run. That's where the problem is. It isn't running. That part of the program isn't running because they did not, you didn't go through you didn't say please, basically, okay? So again, in the field, you're going to learn very quickly how to make online changes. You have to. But for here, for me, please make your changes offline and then compile them and download them, okay? Now with Siemens, it's easier to make those changes, but once you make those changes, it turns from green to not green. In other words, you can't see the nice flow of power through the circuit. It takes it away. So basically what you do is then you go offline, hit compile, download, and then it comes back nice and green. So that's how they do it. And again, I want to encourage you to try to get used to the software, get used to the programming of the software, and both of them. Try both of them out, but realize that there's some, because you're dealing with the real world, there's some caveats, and the caveat basically is, we as a vendor of that software don't want you to do something that you will later be sorry for and you'll sue us for. So if you want to do it, you must say the word please about 10 different ways. And You know, some projects I've worked on that they didn't even have a download to that you couldn't make changes online. Okay, some of the software programs that I've worked on, you couldn't make that, so you had to stop the line. You had to basically make your changes offline, then say, are you to a point where you can stop? Please, may I stop? And then they say, okay, now you can stop. Shut, you know, they stop the line, download, turn the line back on, and then let it run. Now, is that practical in all cases? Absolutely not. There's some situations that you just can't do that in. So you have a different mentality in a factory. And this is part of this course, is thinking in terms of what do I have to do in order to make this program work in the real world? And that's part of on offline programming and online programming. And that's what I'm trying to get over. I'm not doing a very good job, but that's what I'm trying to talk to you about. Okay, in other words, you can do things here that you can't do in the real world. Okay, so this is the gray, the dark gray. That's the Siemens. Okay, and then this is the old Allen Bradley. We don't have these anymore. That's the new Allen Bradley, which is, no, I'm sorry, that's still the old one. This is the new one. This is the one that we have that we use. Now the jumpers that I was talking about are right in here. And you should look and see, if you just have two wires going to this, the outputs are not going to work. So you need to have the two and then the other jumper, and then you'll see if there's no jumpers in here, outputs will not work. So you have to find one that does have the jumpers and mimic that. Most of them do. Every once in a while you're going to find the one that doesn't. Somebody's taken them off for whatever reason, and we have to put them back. Right now, today, the labs upstairs are a mess. We're trying to get them back up to where everything is working and good order. But right now, today, there's a lot of wiring that needs to be done, and we're going to get it taken care of tomorrow and Monday or whatever. But anyway, now this is the TIA programming from Siemens. Okay, now this was taken in like 2012 as version 11. We actually started with the first version that they had in the United States, which is version 10.5. All right, we were actually among the very first people in the United States to teach Siemens in a classroom setting in a university. And by the way, I'm not looking for any accolades for this, but we're still one of the only schools in the country that do this, that teach Siemens and Allen Bradley, and we teach them both in the same course. I strongly believe that because you can do comparison of the two. I can talk about one and I ask you how would you do that in the other one? And those are good comparison questions. And also you're basically getting two for the price of one, because I can teach the two just as fast as I can the one, and they're not that much difference. After you've done this a little bit, you say, what's the big deal? There's not that much difference between them. There is some, but not much. And you can say, well, yeah, but when you go out and you apply for jobs, it pops up that, oh, you've got Siemens. Okay, let's talk about that. So anyway, this is the Allen Bradley. Now, Allen Bradley, you have to click on Studio 5000. So Studio 5000 is the overall program that you use, Studio 5000. And before you do that, you do RS Logics. One time you do RS Links Classic. Do this once. And that establishes the communication. And once it's been done for the rest of the semester, you don't have to do that. Studio 5000 runs, and then you have to choose between Logics and your view. You pick one or the other. And this only attaches to one PLC, and this only attaches to one HMI. You can combine these two by doing a save in the view program of the PLC that it is looking at. So in Studio 5000, you have to choose and you have to go one of two directions. You don't see both of them at the same time. You're doing one or the other, period. Why did they do that? Why did they combine them? It used to just be RS Logic 5000 and then the View. Why did they do that? Because Siemens did it. So if you're a salesman and you keep hearing that, well, Siemens has got them both in the same program, you get tired of that after a while. You take it back to your boss and they tell, oh, we got to do the same thing. So they basically combine it into one thing, but it's really two things, and it's just one of each. But that's okay. You can get along, and it works just fine. And I bet if you price a job in the real world, you're going to come out within dollars of each other. Why? Because they hate each other to the point that they will bend over backwards to try to get a job. So if you're bidding a job and they know that they're bidding against the other guy, they're going to do their best to try to get that job. Once you have a plant that is established as either Siemens or Allen Bradley exclusively, at that point in time they can come in and ask you for list price or whatever. They can jack up their price. But if you have a plant and you have both Allen Bradley and Siemens in that plant, you're going to have both companies coming in there and doing their best dollar for dollar, and they're going to be within dollars of each other. They're very, 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 very big competitive companies. And you say, which is better? I'm not going to say, and I'm going to tell you that just as long as you can say the word Siemens, Allen Bradley's going to jump. They're going to come in and do whatever it takes to get you to do Allen Bradley. But also, if you have a resume that says Siemens on it, your value goes up because you now know both of those two big boys. Anyway, so that's kind of an overview. And again, you get a page and you start programming. There's where you write your program. That's Allen Bradley's program. And you get a page with Siemens and it does the same thing. All right? And you have to wire it. Now there is a doozy. What is that? That is the oldest programmable controller programmer in existence. That's an old picture of a Modicon 084 programming panel. And the reason I put it in there is because I programmed one of these. Just one, but I did program one. And there's your thermal switches. Not that you will ever have to do this, ever, but there it is. Now, what is it about this guy? The program that is running this in the background is an if-then-else only statements. You can actually take and make an if-then-else statement that will execute that line. One if-then-else statement can execute that whole line of logic. And when they said they basically built their whole programmable controller on if-then-else statements, that's exactly what they did. And if you're interested in historically how early PLC vendors did their logic, this is a good example of how they did it to make it easy for them, that you had to restructure your logic to make it to fit their logic, but it's just one if then else. Can you bomb out an if then else statement? No, you can't. You can't lose control of the program counter. You cannot bomb out the program if you only have executing if then else statements. And so at the end of this chapter, it's asking you to do a download. And that's at the end of this chapter, in the video, we go through the download to the Allen Bradley, the download to the Siemens. And realize that this is the old Siemens, not the new Siemens. And I think I'm probably talking about version maybe 14 of the Siemens. The Allen Bradley has not changed. We've kept the same version, 32. But the Siemens has changed. But again, I'll go through this more with you later, but that's the beginnings of this. Okay, about out of time. Chapter 3 is in the books, and I want you to just look through this a little bit. There are some of the, at the end of chapter 3 and at the end of chapter 15 are most of the, if something doesn't work, go here first, okay? At the end of chapter 3 and at the end of chapter 15, there's hints, and I probably should organize them better and have a chapter on just, you know, gotcha things that you should look at, but there's some of them right here. Allen Bradley also has another HMI product called Factory View. All right, so they've got the view and then they've got Factory Talk, excuse me. They have two versions, the Systems Edition and the Machine Edition. We have that version on the computers in the 2350. So if you're inclined to learn another HMI program besides this, and I would encourage you to learn this one because it's straightforward, it's easy, and I can help you with this one. This one I can help you with as well, but it's an older one and it's, I hate to use the word clunky. It's got some really nice things about it, but I think they're putting their effort into this one. I'm not really sure, but we have this. And we also have the license to another product, another HMI product called Ignition, which I can download because we have 7 licenses for that as well. Not done anything with that yet, but if you're so inclined and you want to do something with Ignition software, it is fairly, that is where most of the companies in the Toledo area are putting their effort today. I'll give you a clue. It's not with either Siemens or Allen Bradley. It's with this third party called Ignition. So there you go. The worm continues to turn. I don't know what to say about that other than I got 7 copies of the licensing if you want to try it out. You're totally confused? Don't be. We can get a handle on this. Once you've typed in a program and get it to work, the one at the end of chapter 4 is the first one. You can do it both Allen Bradley and Siemens. That's 2 points and 2 points. That's 4 points. That's 1/10 of the way there. Once you got the Siemens running, you can do it in Siemens. That gets you your mind spinning a little bit, and hopefully that helps. Take care. See ya. Have a good weekend. So start.